Hi, my name's Dr. Peter Kay, and this is the next lecture in the module Automotive Engineering on the internal combustion engine. If you have any comments, queries or questions about any of the material in this lecture, then my contact details are here. Please email me or come and see me. So this is the fourth lecture in this series, and this is on gas exchange. If you haven't seen any of the three before this, then I suggest you go back and look at those before this one. Okay, so the contents of this particular lecture. I'm going to talk about volumetric efficiency. I'm going to define it for you and talk about how it impacts on engine performance. And this is really what does kind of drive engine performance, and we'll see that later. I'm also going to talk about flow through valves, what limits flow through a valve, and also how it can be maximized. Valve timing, I'm going to introduce the concept of that and again how it impacts on engine performance. And finally going to talk about supercharging, introduce it, and also talk about the factors that impact on compressor performance. Okay, so first, just talking generally about the gas exchange process. So what we're really talking about is the ability for an engine to move the working fluid, air in this instance, in and out of the engine. So the engine's performance is air limited. It's relatively easy or relatively trivial to get fuel into the engine. We can squirt more into the intake manifold, or in the case of a direct injection engine, we just squirt more fuel directly into the cylinder. That's easy enough, it being a liquid. But to get more air into the engine so that we can actually burn that fuel, that's what's really limiting the performance of the engine. And engines are usually optimized for maximum power at high speed, sort of cruising down the motorway. And there are a lot of things to consider depending on the type of operation. Four-stroke engine, primarily interested in volumetric efficiency, and we'll define that on the next slide. Two-stroke engine, scavenging efficiency is very important because you obviously need to exhaust your products and get your fresh charge into the cylinder, all in the same thing. And just in general, there's some considerations which I'm not going to cover in this lecture. The charge motion control, so what's the air doing in the cylinder, whether you've introduced tumble or swirl or squish or whatever. Tuning, how you tune the intake manifold and the exhaust manifold and all the runners to improve your volumetric efficiency, and also noise. So what is volumetric efficiency? Well, first, take a step back. So the intake system, if you remember from the first lecture, it's made up of several components. We've got the air filter, the throttle plate, the intake manifold, the intake port, and the intake valve. Now, all these components, important as they are, what they're really doing is they're just restricting the amount of air that you can get into the engine. They're all creating pressure drops, or which is inhibiting the airflow into the engine. So what the volumetric efficiency is, and we talk about it, it's called volumetric efficiency, but strictly speaking it's not an efficiency. But what the volumetric efficiency is it's the ratio of actual mass, so the mass that you can actually get into the cylinder, divided by the theoretical mass of the air that you can get into the engine at atmospheric conditions. That's important. So it's displaced by the piston. So here we got the formula here. So the volumetric efficiency is equal to the mass of air as a flow rate divided by density to get into a volume, times by the volume displaced by the engine, times by number of revolutions. And there's a 2 on this top because this formula is for a 4-stroke engine, so you're only intaking once every 2 revolutions. Or that can also be expressed as, rather than this sort of dynamic, if I can say it like that, way in that if you could just measure the amount of mass in the cylinder, then it's simply the volume of air in the cylinder divided by the volume displaced. But this one here is the one that's more commonly used because you can measure it's easier to measure mass air flow rates and revolutions per minute. So the air density is important. It depends which one you use, because the air is a compressible fluid. Its density will change with both temperature and pressure, so its density is going to change all the way through the intake system. So it's important to clarify which density you're talking about. So if you're talking about the air density in the manifold, then you're talking about the volumetric efficiency between the manifold and the engine. If you're talking about take the air density, the atmospheric air density, then you're talking about the volumetric efficiency of the whole air intake system. And volumetric efficiencies tend to be pretty high in naturally aspirated engines, around between 80 and 90%. However, it should be noted that for turbocharged engines, and we'll come on to this later in the lecture, the volumetric efficiency can actually be greater than 100% because you're pressurizing the air into the engine. So, and as I say, we'll talk about that later. So we can get efficiencies greater than 100%. Now, I put this plot up. I make kind of don't really make any apologies, but this is taken straight out of Internal Combustion Engine Fundamentals by John Hayward. And up to now, I've kind of tried to stop myself from putting up just taking things from the book, but I thought this plot was so good and it explains volumetric efficiency so well, I couldn't really see any other way of explaining it. So what we've got here is got volumetric efficiency on the x-axis and mean piston speed on the y-axis, which is obviously just you can convert to revs per minute or per second. So what this plot is saying is curve A, or rather this is line, this is really what you want. Why can't we have this high efficiency across the whole range of speeds? What's happening here? Well, actually, we're saying at low speeds, because we at lower engine speeds, the air has a longer residence time in all the air intake runners. So the air actually heats up as it goes into the engine. As it heats up, its density decreases, so the volume in the cylinder is less. So you'll lose in volumetric efficiency due to charge heating, and that is more pronounced at lower RPMs because of a higher residence time. So instead of having curve A, we move down to curve B. But we've got lots of other effects on here, and hopefully see how this plot's working now. So we move from curve B down to curve C due to flow friction. Now the friction in the pipe changes with the square of the speed, so the flow friction is higher for higher engine speeds. So that's why you can see the bigger drop up here compared to up here. And once we start getting to really high engine speeds, then the flow in the pipe starts to choke, which, if you remember from your fluid dynamics, is can happen depending on the pressure ratios. So we get choking at high speeds, so that drops us from curve C down to curve D, which is this one. Now we do get some payback here. So what we can also say is at these high speeds, because the air in the intake runners is still moving as we're kind of shutting it on and off, we actually get a bit of a ram effect. So this is forcing air into the cylinder at these high speeds. So we're saying that we go from curve D up to curve E, and with some tuning, we're saying that we can get from curve E up to curve G, and eventually we get to which is a solid black line. So this is kind of our curve. So because of all these competing effects, because of charge heating, sorry, I didn't mention backflow. So at very low speeds, because the pressure and intake manifold will actually be lower than the engine, than the pressure in the cylinder, you actually get flow going back out. But because of all these effects, tuning, friction, choking, ram effect, etc., this is what actually we end up with. So this is volumetric. This is why the volumetric efficiency takes on this shape with piston speed, and you can see that this looks very much like the torque and power curves that you get, and that's because, going back to the start, it fundamentally comes down to the amount of air that you can get into a cylinder. Okay, so moving away from the volumetric efficiency, we're now going to look at the flow through valves. So got a valve over here. This is the intake runner. The valve is in the middle. You can see it's lifted off some lift LV. It has a head diameter of the valve, an inner seat diameter, and also a stem diameter. Now the mass flow rate through the valve will depend on how high the valve is lifted. The mass flow is rho AV, so rho density of air times the area times the velocity of the air. But which area do we use? Well, that area depends on how high the valve is lifted. At low lifts, you can use the curtain area. So the curtain area is kind of this area here. So if you think that the valve is lifted and it's basically created a curtain like an annular ring, and that's equal to pi d, which is the circumference of the valve, times by LV, so gives us that curtain area. But the port area at high valve lifts, this will be the restriction area, this area across here, and that port area is equal to the pi r squared, but you've got to subtract the stem diameter from that as well. So it depends whether we got the valve is lifted a lot or little. Depends on which valves, on which area we use, because lifting the valve doesn't always give us more flow, because eventually the area of the curtain will be greater than the area of the cross-section area of this pipe, and then that will be the limited value. So as I say, when the curtain area is equal to the port area, then this is a limiting factor. So if we equate those, so say that curtain area is equal to the port area, then if we rearrange that, we can work out what the lift will be when this condition's met. So rearrange that, and we end up with the diameter of the port minus the stem diameter divided by 4 diameter of the valve. Now if we just make some assumptions here, so if we just assume that as the stem diameter goes to 0, so that term will disappear, and as the diameter of the valve approaches the diameter of the port, then eventually we end up with this, that the valve lift for when the area in the port is equal to the area of the curtain is approximately equal to the diameter divided by a quarter. Sorry, divided by 4, 25%. Okay, now the flow that you get through that area won't necessarily be the flow that you get, and this is because for any flow through any nozzle or any pipe, there's some associated discharge coefficient, and a discharge coefficient is the actual flow that you have divided by the theoretical flow that you could have. And I've got three kind of valves here to show that. So if you look going from this one to this one to this one, the valve is actually lifting more off the seat. So at this relatively low lift, you can see that the air, represented by these blue arrows, is hugging the walls and the valve respectively. So there's no flow separation. So as we increase our airflow through this valve and our Reynolds number, the mass flow rate through this valve will increase. But eventually we get to a point where the flow will separate from the valve. So what's happening here is the flow gets so high that it no longer kind of hugs this line. We get a turbulent recirculation regime in here, and the flow separates. Now that effectively acts as a restriction in this area here, and will reduce the discharge coefficient and the amount of flow that can flow through that valve. And if we increase it, if we lift it further, then it will start separating from the intake port as well as the other side, and we'll start restricting the flow even more. So the flow separation reduces the discharge coefficient, but there is some good design that we can do to reduce the effects of that, and the discharge coefficient can be increased by rounding the valves. So rather than having these sharp edges as shown in my illustration, if the valve is rounded off, that will give the flow a better chance of sticking to it and not causing recirculation zone. Careful selection of the angle of the seat angle is important. The angle seat is the angle of this to the horizontal, and by choosing a nice by choosing that angle, that will again help the flow, prevent separation of the flow. And also the upstream pipe work has a very big effect. If there's no nasty 90-degree bends upstream, that's going to not disturb the flow either. So all these factors can be included in the taken into account when designing the intake system to help minimize flow separation, to help increase the amount of flow into the cylinder. Okay, to illustrate the flow through the valves and how kind of complex it is, I've included this video which was taken by the Engine Research Department at University of Brighton. I'll just explain what you're looking at before I run the video. So this is basically a mock-up of a piston made out of perspex or transparent material, and the piston is here. You can see the intake and the valve stem and the valve here, and what you're looking at is why you can kind of see the air, if you like, is because this is being illuminated by a laser. There's a laser over here which is kind of shining in this way, and it's illuminating all these particles which are in the fluid. And I say fluid because what's really here in this instance is it's probably water, some kind of liquid, and this is quite common method for trying to understand flow phenomena in engines, is rather than looking at the air, because it's happening very quickly and it's quite hard to seed it and to measure it, is to actually replace the air and with a liquid such as water. That has a number of advantages. Firstly, it means that you can seed the water with kind of small particles which you can illuminate with the laser and you can see. But secondly, it means you can run the engine much slower, so you can see what's going. And let me just explain that. The reason you can run it slower is because of what's called Reynolds scaling. So if you remember, your Reynolds number is equal to density times some scaling parameter times velocity. Now the density of water is 1,000 times that of air. So for the same Reynolds number, which means that you've got the same flow regime, you can run the velocity can be 1,000 times slower if you're using water rather than air. So it means that you can see what's going on. So anyway, what you're going to see in this video is the piston's going to come down, and you'll see the flow into the cylinder and the recirculations and how complex that is. Then what you'll see is as the piston's coming back up, you see the valve open again, and you'll see the flow back out of the port. Okay. So hopefully you can understand how complex this is, and all the rather than just getting flow in and out, it's a lot more difficult than that. And all this kind of turbulence in here that's going on in here, that's helping, if you think in a real engine, that's helping mix all the air and fuel together prior to combustion. Okay, in terms of valve design, often you'll see that engines have multiple valves. So rather than just one inlet valve and one exhaust valve, they have two or possibly more depending on the engine design. So what are the advantages of having multiple valves? Well, there's a number of advantages. Firstly, because you've got more, because you're doubling up, it means you can have, for the same area, you can have smaller valves. Smaller valves mean smaller mass, and if you think about the valves, they're reciprocating in the same way the piston's going up and down. The valves are going up and down. So you have a lower mass, smaller reciprocating mass, less stresses on them, more simpler and less stress on the whole valve train. You can also have increased heat transfer to the cylinder. These valves also play an important job. They are transferring the heat that's being convected onto this through the valve seat into the cylinder head and into the coolant. There's no cooling on the valves, so it's important in terms of heat transfer as well. And also, it gives you an advantage in terms of the engine design. If you open your valves at different times, it means you can create, depending on how well you design it, all kinds of different flow regimes within the cylinder, which is going to increase turbulence and increase your mixing in the cylinder. However, as with any engineering problem, there are some disadvantages. So the disadvantages of this are, firstly, you've got more components. So overall, although each valve is going to be lighter, there is going to be a higher overall mass and associated cost with that. At low RPM, it can produce less torque, and the reason for that is because you've got effectively a larger flow area. It means that the velocity, for the same mass flow, the velocity is going to be lower, and because if the velocity is lower, you're going to get poorer mixing, and that poorer mixing is going to give you poorer combustion. And the last thing I just wanted to point out here is the exhaust valves are smaller than the intake valves. So it's the exhaust valves on this side. Let's draw those. So these are the exhaust valves here. These are the intake valves on this side. Now, why are they smaller? Well, there's a very simple explanation for that. During the exhaust stroke, you have higher pressures in the cylinder than you do in the ambient atmosphere. So because you've got a higher driving pressure, you don't need the same area, because you'll get the same mass flow through a smaller area because of the higher pressure ratio. So basically, that's the simple answer to that. It just comes down to a pressure differential. Okay, so valve timing. This plot shows a typical valve lid profile with crank angle degrees. So we're going from top dead center through to 360, back up to 360, and back round to top dead center. We've got valve lift plotted up here for an exhaust valve, for the exhaust valve, and the intake valve. So you can see the exhaust valve opens before bottom dead center. It opens, it closes, and the intake valve opens before the exhaust valve shuts, reaches its high valve and comes back down. So you can see clearly here in the middle, we've got this kind of overlap area here, where for a certain time between these crank angles, we have a valve overlap. Now, this is quite important because if you think in terms of what you're trying to do in the engine, at this point here, we're trying to this is the compression stroke, and from here to here is the intake stroke. So here, by the end of here, we want to exhaust all the gases, and here we're just intaking fresh charge. So at this point here, this overlap, both the valves are open, and what you're really trying to achieve is you're trying to achieve a flow where the flow of the incoming air is effectively pushing out or scavenging the exhaust products to eventually this point where it shuts. And the point where it shuts here should just be when the fresh charge is getting to the exhaust valves, because you obviously don't want to lose any of that fresh charge that you're inducting. But that's the reason for the valve overlap, is to try and improve the scavenging and not trapping any residual gases in the cylinder prior to the intake stroke. This is explained a bit better, and I'll go through each of the valves, the inlet and the exhaust, and talk about the opening and closing times. And this is kind of more typically shown with this kind of dial, if you want. So we got top dead center, again going around to 90, bottom dead center 270, and then back up to top dead center. So what I've got shown here is kind of a say like a radial representation of what was on the previous slide. So start during the compression stroke, sorry, the exhaust stroke. So the exhaust gases are squished out, and then as we approach top dead center, the inlet valve is opened, the exhaust valve closes, we intake round, and then we have our compression and ignition cycle before it goes back round again. Now, as I just said on the previous slide, typically the exhaust valve opens around about 40 to 60 before bottom dead center. Now, the later that we open that, then we extract more power from the stroke, because this is our power stroke. Remember, this is where the products, the combustion is going on. So by opening it early, we're just losing power. So you want to open it as late as you can, and as close to bottom dead center as you can, to increase efficiency. But at the same time, we need to help our combustion products escape. So if we open it too late, we're not going to have sufficient time for all the exhaust gases to be expelled before we're trying to bring into our next charge. And also, if you think, once the pistons come down to bottom dead center, so it's being pushed all the way down to bottom dead center, once it gets here, work is being done on it to get it back up to top dead center. And if you still have a significant amount of pressure in here, then you need more work to do that. You need more pumping work to do that. So by opening it early, you've reduced the pressure by the time you get to here before you have to pump the exhaust gases. So there is a compromise. So at high load, you want earlier opening times, and at part load, you require later opening times. So with anything, it is a compromise. Now, for the exhaust valve closing, this typically occurs around 15 to 30 degrees after top dead center, around about here. Now, you'd want to close the exhaust valve as late as possible, because this would maximise the time for the exhaust product to be completely expelled from the cylinder. And also, by opening it as keeping it open for as late as possible, it will also minimise the compression of any exhaust stroke. And remember that these valves don't open and close instantly, so it's not closing here. This is when it is closed. so the lift is reducing all the time from probably about here. So actually here it's as good as closed, because the flow area is so small in a way. Now, in terms of early closing, you might want to close it early, if particularly for port fuel injection, because you're bringing your air and fuel into the cylinder together. You don't want that to basically come straight in the intake, through the intake valve, straight across the combustion chamber and straight out of the exhaust valve. So that's might be why you want to have early closing, but really trying to go as late as you dare to maximise the exhaust products. For inlet valve opening times, so this typically occurs 10 or 20 degrees before top dead centre, round about here. So the valve is opened before top dead centre, so that it is opened by top dead centre. So as I said on the previous slide, these valves don't open and close instantly. So to maximise your intake, you want the valve open, or as open as it can be, by top dead centre, to really maximise that intake stroke. This is how you're going to get the air into the cylinder. So you really want to improve that. So that's why it's open before dead centre. It also gives you the advantages that we mentioned of good scavenging across the combustion chamber. Now, the reason you might want to have late in inlet valve opening is if you're running at particularly low RPM, and the pressure, you get a backflow of exhaust pressure into the intake manifold. So with this overlap, you might want to have late inlet valve opening if on the design of your exhaust system you're getting exhaust gases coming back through and getting exhaust residuals into the intake manifold. So the inlet valve closing then, so we've opened it, induction stroke, and closing it. Now this is typically between 50 and 70 degrees after bottom dead centre. Now the reason why you want this to be closed as late as possible is to really allow fresh charge to continue to flow into the cylinder. So you might think, well, why doesn't, how's flow still flowing into the cylinder? Again, think back to kind of the flow in the intake run has got inertia. So once it starts flowing, it's got that momentum. So even though the piston has gone past bottom dead centre and is starting to compress the gas in the cylinder, you've basically pulled a vacuum in the cylinder during this intake stroke to bring air in. So air can still continue to flow into here even though you're compressing it, because of the pressure differential between the two. So this will increase your volumetric efficiency at high speeds, when you've got high inertia of the air coming into the cylinder. The reason why you might want to close it early is at low speeds, when you haven't got that high speed air or the high level inertia in the intake manifold, and you're at risk of flow basically flowing back out of the cylinder into the intake manifold. Okay, so we talked a lot now about the valves and getting air into the engine, and so far we just kind of talked about naturally aspirated engines, where using valve timing or the tuned air intakes to get air into the engine. But another way of doing that, kind of a mechanical way of doing it, is to actually increase the air density of the air going into the engine. So there's two common ways of doing that. There is supercharging, or mechanical supercharging, whereby a compressor is driven directly off the drive shaft of the engine via some sort of gearing arrangement, and the intake air comes into the compressor, is compressed, that comes into the engine, and then it's just exhausted out. So as I say, the compressor is driven directly from the engine. This has the advantages that there's no lag. Because the compressor is driven straight off the engine, it will just, as the engine speed increases, so will the compressor. It will spin as it will increase in speed as the engine increases in speed. But you do have a overall reduction in efficiency, because what you're doing is you're actually taking, because you're effectively driving another piece of machinery, that's power that would otherwise be transferred to the wheels. So you're reducing the overall efficiency of the compressor by doing that. The other way is turbocharging. So the way that this works is the intake air comes into the compressor, and instead of using the spinning the shaft of the compressor from the engine, it's actually spun by a turbine which utilises the exhaust gases. So when the exhaust gases come out of the engine, as I say, they spin up this turbine and they're exhausted to atmosphere. This is connected via a common shaft which drives the compressor. Now there's the disadvantage of this is that you have a turbo lag. So as the engine speed increases, there is a lag between for the time of the exhaust gases to basically overcome the inertia of the turbine to spin that up, which will then in turn spin the compressor up. So there is a lag between when you demand the power and when you actually get it. But it's a higher efficiency compared to the mechanical supercharging, because you're not extracting any of that power from the engine. It's what would otherwise be waste heat or waste gases. So it's a higher efficiency than the mechanical supercharging method. So turbocharging compressors typically use centrifugal compressors, tend to be higher efficiency, and they're made up of an inlet casing, and then a rotating bladed impeller in the middle, a stationary diffuser, and then a collector which feeds it into the engine. So this is an example of the turbochargers we saw in the previous slide. So you've got the compressor on this side and the turbine on this side. And centrifugal compressors operate at a higher efficiency for higher angular speeds. So the faster you can spin them up, then the more efficient they are. But that's to a certain point, and we'll cover that on the next slide. Here's a cutaway of a compressor here, so you can see the compressor and the turbine on this side, and the bearing and its lubrication system in the middle. Okay, for each compressor, there is kind of the characteristics of that compressor is described by a performance map, and that's shown on this side. So what we've got plotted here is the pressure ratio. So that is the pressure of the air exiting the pressure of the air exiting the compressor divided by the air going into the compressor. So the atmospheric pressure. And on the x-axis we have the mass flow rate. And what we've got here is we've got plotted two things. We've got plots of speed. This is compressor speed, and also in the middle we have sort of so-called like islands of compression efficiency. So you can read this map in a few ways. So these black lines here are engine speed, and this is compression efficiency. Now, if you say we're here, and you were to reduce the mass flow rate of the, so let's draw it on. So just say you're at this point here, and you were to reduce the mass flow rate through the compressor. Eventually you get to this point here. Now this is called the surge line, and what happens at this point is, think of the compressor, the blades on the compressor, as wings on an aircraft. Basically you're reaching a point where the aircraft wings, or the rotor blades, are stalling, so they can't actually compress the fluid because there's not enough air flowing through the compressor, so you kind of get a stalling. So this region is unstable here. You can't really operate in that regime. And likewise, if you go the other way, so starting from the same point, and you were to increase mass flow, eventually you get to this point here, and this is the choke line. So what's happening here is you've got, going back to our compressible fluid dynamics, you've got so much air going through the compressor that eventually it chokes, and you just can't physically get any more mass flow rate through the device. So there are compromises. So it's not just as easy as sticking a larger turbo on your car to increase the pressure, because you might be operating in an unstable regime, and if you put too small one, you'll be choking. So you've got to look at these compressor maps when deciding which one needs to be fitted. Okay, so hopefully in this lecture you now know what volumetric efficiency is, its importance, and how it impacts engine performance in particular, and how you could see the similarity between the volumetric efficiency with speed and the power and torque curves that you get on the dyno. We also talked about flow through valves, what limits the flow, and how just increasing valve lift doesn't always give you more air, and how the flow can be maximised by improving the flow through the valves, such as rounding the corners and trying to increase the discharge coefficient. Valve timing, talked about why the correct amount of overlap between the exhaust and intake valve is a good thing, and how advancing or retarding the valve timings of each of whether they're opening or shutting, and what impact that has on the engine. And then finally we just talked about supercharging, so the fact that we can increase the density of the air to get more air into the engine, a higher mass of air into the engine for the same volume, and what factors affect the compressor performance, such as stalling and choking, etc. Well, thank you for listening to this lecture. The same, my contact details are on here. If you have any comments or queries, please come and see me. Thanks.